Welcome to our deep dive into urban traffic flow and the transformative power of synchronized traffic lights. Today, we're exploring the intricate probabilistic models that could revolutionize our streets. Efficient traffic flow is the lifeblood of urban environments. Central to this are traffic lights, but the traditional view of vehicle arrivals as independent events at a traffic light might be flawed. Let's break down the math. Our study challenges the independence assumption using Poisson and Bernoulli distributions. The Poisson process models the arrival of vehicles. It's defined by a key parameter, lambda, representing the average number of arrivals in a given time frame. In our observation, we studied a busy intersection during peak Thanksgiving rush hours and the arrival of vehicles during different light phases. For green lights, lambda green was calculated as 20 vehicles per 1.1 minutes, or 18.18 vehicles per minute. This high rate indicates a rapid influx of vehicles during green lights. Conversely, during red lights, lambda red was lower at 5 vehicles per 2.1 minutes, or 2.38 vehicles per minute. Now, let's talk about the Bernoulli distribution. It's a simple yet powerful way to model binary outcomes. In our case, whether a car passes or stops at the light. With an average of 20 vehicles per green and 5 during red, we have a total of 25 vehicles. If the intersection's capacity is less than this, say 15 vehicles, we calculate the probability of passing as 15 over 25, or 60%. The remaining is 1 minus p, or 40%, which is the probability that a car stops. Enter AGLEA, our adaptive green light extension algorithm, a solution to traffic synchronization. This algorithm dynamically adjusts green light durations based on real-time traffic data. AGLEA starts by calculating the expected number of vehicles during the green light phase, expectation of green, using the Poisson parameter lambda green, and the standard green light duration t green. If the expectation of green exceeds the intersection's capacity c, we need to extend the green light. The extension, delta t, is calculated as expectation of green subtracted by our capacity, all divided by the service rate, s. The service rate is the maximum number of vehicles passing through in a given time frame. This extension is capped at a maximum allowable limit to ensure traffic balance. In practice, if we observe more vehicles than the intersection can handle, AGLEA extends the green light just enough to clear the excess, optimizing the flow and reducing congestion. AGLEA is a blend of probabilistic rigor and practical application. It's a testament to how advanced mathematics can lead to real-world solutions in urban traffic management. For further exploration into this, we can delve into studies on intelligent traffic flow, light control, and adaptive signal control technology. These are the building blocks for a future of efficient and responsive urban transportation. Thank you for joining us in unraveling the probability behind traffic light synchronization. Together, we're paving a way for smarter, more efficient urban streets. We will now perform an application of AGLEA using real-world numbers as a bonus. The first step is simply calculating the expectation of green, which we already know given our lambda is 18.18 cars per 1.1 minutes and t green is 1.1 minutes. Multiplying these two numbers together gives us an expectation of 20 cars. Next, we know that since the expectation of green is greater than our capacity, 20 is greater than 15, we simply use delta t to calculate this. Our s is our service rate, which is 15 over 1.1, and putting all these numbers together, we get an additional 0.37 minutes that need to be added on. Next, we have to adjust our green light duration, adding it to our original 1.1 minutes, and creating a new number of 1.47 minutes for the duration of a. For the next cycle, if more cars are observed, adjust lambda green and lambda red accordingly. Repeat the process for each cycle, using real-time data. In the real-world implementation, traffic sensors would provide the actual numbers of cars arriving and passing, allowing for more precise adjustments of lambda green, lambda red, and delta t for every cycle.